I will begin. Read a scripture here to get started. So this is Psalm 37. Psalm 37, verses 5 through 8, I think. Commit your way to the Lord. Trust also in him, and he will do it. He will bring forth your righteousness as the light, and your judgment as the noonday. Rest in the Lord and wait patiently for him. Do not fret because of him who prospers in his way, because of the man who carries out wicked schemes. Cease from anger, forsake wrath. Do not fret. It leads only to evil doing. So I'll stop there. But let me begin with a word of prayer. So, dear Heavenly Father, we thank you again for this class. I thank you for this day. I thank you for these students. Just ask you to bless our work. Help us to just understand the derivative as a function today, and just help the students to make sure they ask good questions as they think of them. Lord, in your name I pray, Lord Jesus. Amen. All right, so let me give you the definition. If f is a function, if f is a function, then we define f prime to be a function whose value is given by f prime of a is equal to the limit as h goes to 0 of f of a plus h minus f of a over h. I suppose I probably, to be fair, furthermore, if a is a left or right boundary point of the domain of f, then we modify the limit as appropriate. And so you probably can figure out what I mean by that if I just draw two pictures, right? So like let's think about a left boundary point might look something like this here, all right? And maybe a right boundary point looks something like that there, right? And so if that were the case, if we wanted to talk about the derivative right there at such a point as this, then in that case I would define f prime of a as the limit as h goes to 0, all right? Well, I guess maybe, I think I prefer actually here, I prefer the x goes to a formalism. So let's say x goes to a from the right of f of x minus f of a over x minus a, right, for that one. Whereas for this one, I would define f prime of a at this boundary point to be like limit as x goes to a from the left of the difference quotient. See, because for these functions, I don't even have values of the functions defined necessarily past the boundary point, so I can't really very well formulate the difference quotient in that way, right? But we would like to talk about the derivative at endpoints. It does have a natural meaning in terms of, just the tangent line being extended past the function, right? So, okay, anyway, that's it. The function is defined pointwise by the derivative, right? So let's look at some examples. So if you think about it, like yesterday, we worked out a few of these actually, right? If we had f of x equals to x squared, we saw that f prime of a was equal to 2a, right? So that tells me that the derivative function, f prime of x, is actually equal to 2x. If I just go ahead and use what we did last class, right? Let's see if I can remember another one. What else did we do? We did, last time, what did we work out? Did we do cube? I think we did the cube, right? F of x equals x cubed. We worked out that f prime of a was like 3a squared. From that, I can tell you the formula for the derivative here, the derivative function, is 3x squared. All right. So it's kind of hard to tell the difference between what we were doing yesterday and what we were doing today. I mean, but there's a sort of a philosophical difference in that now I'm saying, think of the derivative as a new function in its own right. All right. In the same way you might think about like 3 times the function as a new function or something. It's a, you know. All right, so let's see here. If I can come up with another example for us. How about this? Example 3. What if we had f of x equals to 1 over x? Well, we could calculate the derivative function. If we calculate f prime of a, well, let me show you. Fine. You know, I'm going to do it a slightly different way here. How about this? I'm going to calculate f prime of x directly. Here's a way to calculate f prime of x directly. You can calculate f prime of x directly if you use the h formalism in the following sense. So like this is the limit as h goes to 0, right, of f of x plus h minus f of x divided by h. So if you just want sort of one-stop shop definition of the derivative, there it is. Right? There's the x already in there. You don't even have to change from a to x. See, I mean, it's kind of a silly thing. I worked it out at a yesterday. Why do I work it out at a rather than x? It's so that we have the freedom to either use the h limit or the x limit without confusion. Right? You can't calculate f prime of x using the x approaches a formalism directly. Because then the x's would get confused. Anyway, you shut up. I have no words. All right, limit as h goes to 0 of, I'm going to pull 1 over h out front, what we're up against here is 1 over x plus h minus 1 over x. Right? But make a common denominator, what do we got? One over h, right, times x minus, parentheses are our friends, x plus h, divided by x plus h, times x. Does anything cancel here? Yeah, let's see, oh no, x plus h does not cancel. No. This is, to quote Dr. Sprano, bad algebra. Like we cannot cancel that because we have to factor out, right? But what we can do is cancel x with x. Now I will cancel this marker. I was trying to go off the bounce. Too much. So the x's cancel, and that leaves us an h here and an h here, and those reduce, right? So the algebra here, and sorry, I'm running on a whiteboard, otherwise I'd write more steps here, but I just want to try to finish this here. That simplifies to minus 1 over x plus h times x. See, because the x is plus x minus x, and then we got minus h upstairs, but h downstairs, they reduce to give minus 1. And that leaves me that, which then I can evaluate as h goes to 0, I get what? I get minus 1 over x squared. So there you go. That's the formula for the derivative function for that. It'd probably be good for us to graph both the function and its derivative to try to understand the relation between the function and the derivative function. What are the relation between the function and the derivative function? Right? That's a pretty standard like test question in Calculus 1. This part of the course is like, here's the graph of the function, graph the derivative function, right? You should be able to graph the derivative function even if you're not given a formula for the function, right? From the graph alone, you can do it. So I think it's helpful, good for us, to graph, maybe start with example 1. So graphically, example 1, what I'm going to do is I'm going to graph the function in blue. This is example 1. So here we're looking at y equals x squared, right? And then next I'm going to graph the cube, which is something kind of sort of like that. There's your y equals x cubed, right? That's, for this one, f of x. For this one, that's f of x for my example 2. Example 3, I'll do over here. Let's see here. The reciprocal function, it looks like this. All right, so there you got your y. It's 1 over x. That's my f of x for example 3. All right. Now what? Well, what's the graph of the derivative function? So the graph of the derivative function is simply y equals 2x for the parabola. So y equals 2x is something kind of sort of, that was supposed to be a line, my apologies. Y equals 2x, that's f prime of x in this case. This one, 3x squared, looks more or less like that. That's f prime of x for that one. And this one here, we've got minus 1 over x squared. What's the graph of minus 1 over x squared look like? It's got a vertical asymptote. It drops down to minus infinity at 0, right? It's like an infinite well. Bottomless pit, right? So it looks something kind of sort of like this. Right. So by the way, another notation we oftentimes use is instead of f prime, you can also write df dx. That's another notation for the derivative function, right? I tend to side more towards df dx going on here because it's just so easy to lose a prime. You know, like primes are easy to miss. It's pretty hard to miss a df dx. But anyway, so that's the different. You know, this is the connection of a function and its the graph of its derivative. Let's talk through it. What does it mean? So the function is decreasing, right? If the function is decreasing, the derivative function is negative. When the derivative is 0, that's where the function has what's called a horizontal tangent, slope 0, right? Then the function's increasing, the derivative is positive. Same story here. This cubic function's always increasing, actually, right? And it happens to have a point where it, you know, has horizontal tangent right there. I think technically it's still increasing there, actually. Because increasing is something we have to define on an interval. We can't define increasing at a point, technically speaking. So as long as you're talking about a pair of points, it's still the case that the cubic is increasing. But it's everywhere increasing, and it just slows down most at 0, you know, in terms of its increase. And then this guy is always decreasing. See that? It's always decreasing. It's decreasing more and more and more and more and more and more and more as it approaches 0 from the left. And it's still decreasing more and more and more and more as you go to the right, because the graph rips from minus infinity up to infinity like that. And so it somehow manages to always be decreasing, right? Any questions? Right. A theorem we should prove in here, because it helps us understand what is and what isn't in terms of functions and their differentiability. One of the basic things we can prove about a function is if it's differentiable, it must be continuous. So let me write that theorem down here. Theorem. If f is differentiable at x equals to a, then f is continuous at x equals to a. Or in short, differentiable implies continuous. All right? So, all right, let's talk more about what these words mean. So this saying that the f prime of a, which is the limit as h goes to 0 of f of a plus h minus f of a divided by h exists, right? So to say it's differentiable at a means that the limit of the difference quotient exists. What does it mean to say f is continuous at a? So this we can capture by saying the limit, my default is to say the limit as x goes to a of f of x is equal to f of a, right? By the way, let's limit the discussion to an interior point. This discussion could be reasonably extended, but pretty much the same calculation I'll show you at a left or right endpoint, okay? But let's just focus on an interior point, so I'm just writing double-sided limit. Now that, I kind of prefer to look at continuity. There's another version, which is just this. Equivalently, we can say the limit as h goes to 0 of f of a plus h is equal to f of a. See, that's an entirely equivalent characterization of continuity of the function at the point, right? The limit as h goes to 0 of f of a plus h is equal to f of a. So again, like intuitively speaking, what's a continuous function? It's one for which, you know, the values of the function at the point in question, they don't just jump. The graph doesn't rip apart at that point. The points on the graph are adhered together. They're kind of glued together in the natural way. Continuous. Now, how do we improve this? Well, I don't know. My preferred way of proving this requires something called the theorem of Carr-Theodori. But the theorem of Carr-Theodori, I'm putting off until after test 1, so I don't want to put that on you guys. So we need to find a proof here which is kind of just involving the things we have. So let's start with what I'm trying to prove. H goes to 0 of f of a plus h. Actually, let's trade that. Instead of looking at that, okay, so that, if this, all right, so let me write it out here. If we had this, if this is equal to 0, right? If the limit of f of a plus h minus f of a is equal to 0, right? If that is true, then what? This is, see, this is equivalent to that, right? Because the limit as h goes to 0 of f of a is just equal to f of a, because the limit of a constant is a constant. So I can trade the desired limit for this 0 limit, all right? And then, so notice the limit as h goes to 0 of f of a plus h minus f of a is equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h times h. So far, I haven't done anything except divide and multiply by h, right? Which I can do inside the limit because the limit considers h close to 0 but not equal to 0, right? Then I can use the limit laws. Why can I use the limit laws? Well, the reason I can do that is because we're assuming that the function is differentiable, which is to say that the limit of the difference quotient exists, indeed is finite. And how about the limit as h goes to 0 of h? How's that work out? What's the limit as h goes to 0 of h? Not a trick question. It's what? 0, right. So this one is f prime of a, and the other one is 0. What's 0 times f prime of a? So this is equal to 0. Consequently, the limit of the difference of f of a plus h and f of a is 0. Hence, the limit as h goes to 0 of f of a plus h is equal to the limit is equal to f of a. Consequently, the function is continuous. All right? So, if you're given a graph of a function and you're asked about the derivative, you know, at a point, let's suppose I had something like all right, so here we've got like y equals to x minus 2 for x. Oh man, that's not right. I'll get it eventually. Maybe it's a half x minus 2. Let me try x over 2. X over 2 minus 2 for x less than or equal to 4. And then up here, you've got y equals to, I don't know, like x over 2 period. All right? In other words, I'm studying the function f of x equal to, you know, x over 2 for x greater than 4 and x over 2 minus 2 for x less than or equal to 4. So what's the domain of f? By my definition, it's everything, right? I've defined a formula that has everything, right? And what's the derivative? We don't, I mean, in this kind of problem, yes, we could slog through the difference quotient, but we should remember what we're doing. The whole idea of the derivative is it's the slope of the tangent line, right? So, of course, if we work out the difference quotient for a line, maybe that should be my next example. It will be. We're going to have 1/2, and we're going to have 1/2 here as well, right? But that's going to be for x greater than 4, and that's going to be for x less than 4. We cannot say that f prime of 4 is a half. Why? Let me run it through. Here's the logic. If f prime of 4 exists, then, by the argument we just gave right here, f is continuous. But it's not. Therefore, f prime of 4 cannot exist. Does that make sense? So this is one of the applications. If differentiable implies continuous, if we have a point of discontinuity in our graph, that is necessarily a place where the derivative does not exist, at least as a function. There comes a time in engineering you define infinity and things like that, and you start working with things, past functions called distributions. But for now, for this class, for calculus, we deal with functions, and so we're not throwing infinity in as a value and junk like that. So when we have a discontinuous function, the derivative does not exist. All right? Final. You guys are making me nervous with your silence. So like this is a famous function, the so-called step function. Basically, it's 1 when x is positive, and it's 0 when x is negative. It jumps. It's like a switch. You guys remember we used to have switches on walls, at least in other buildings. I miss switches. If you asked what's the derivative of this, in Calculus 1 the answer is it's 0 everywhere except where it's not defined, which is here. which is like this is 0, right? But there comes a place in engineering when you say the derivative of the step function exists. It's called the direct delta function, which is not actually a function. The direct delta function is everywhere 0, except right here where it's infinite, and then it's 0 again. This is delta of x, which is the derivative of theta of x. Now this is not calculus 1. And to make this mathematically rigorous, the mathematics for that was only done like the 1930s or something by a fellow named Schwartz, and there's something called the theory of distributions. So there is stuff past what we're doing in here which actually has application. But for us, if we're dealing with functions, if you have something that's discontinuous, it's just you don't have a derivative for it there, all right? And that's kind of weird, right? Like this direct delta function is such a thing that this infinite spike has area 1 under it. It's weird, right? It's kind of weird. Anyway. At one point in my life, I was taking 2 courses. On the one hand, I was taking a course in real analysis, which is like more picky than what we're doing in here. Like, you know, I like, at the top of the thing, I said C is a real number. In the bottom of my solution, I'm like, A is less than B is less than C, so therefore A is less than C. And then she takes off a point. I'm like, real numbers have the transitive property for inequality. Why did I lose a point? And she's like, you didn't say C was a real number. But I'm like, it's at the top of the proof. We read proofs top down. I could not get my point back. And then I go to my other class in physics, where the professor is asking us what's the derivative of the step function, and then he makes fun of us for not knowing it's this direct delta function, which isn't even a function. You can't have a function which has area 1 under just 1 point. But anyway. So this time I'm filling with meaningless stories about delta functions and step functions. It could be filled with your questions if you had questions. You'd prefer me to talk about this kind of stuff. We do have time for questions if you guys got questions, but I will go on otherwise. I can always differentiate more things. Mm-hmm. Yeah. Preferably about math, yes. Math questions, yes. To be clear.
Look at this.
My community college professor used to tell us, you can come ask us, he said, come ask me questions about anything, about electronics. I'm not a life coach, you know, I'm not here to tell you what to do with your girlfriend or whatever. I do have some advice for dating, but anyway.
Is this possible to do this, to set it up like this algebraically?
Oh yeah, we could work a problem like that. Yeah. Yeah, for that one, you just need to use the, you got to use the limit laws and what you're given. As to whether or not what you're doing was exactly correct, I'd have to sit and look at it for a minute, but, yeah, okay. Oh, I just remembered what I wanted to try today. Sorry guys, I was so proud of myself this morning because I had pizza yesterday and I didn't have any soda, and it's the saddest thing in the world to have pizza without soda. You know, it's just not right. So today I put a soda in my backpack. I was like, yes, I remembered. It's gonna be a good day. Because I got 2 more pieces of pizza. There were 4 pieces yesterday. I didn't need 4 pieces. But then I also put an adapter to charge my electric bike in my backpack in the same compartment. What happens when you put a can of Coke and a adapter in the same? Yeah. Now I get to the office, I'm like, what's this? Oh, this must be Coke. Now, all is not lost. I still have like a third of the can. So, and I put a piece of tape over it, so hopefully it'll hold till lunch. So anyway, I'm a little bit distracted today. So yeah, which number was that you're asking me about? 101. So yeah, so like, oh, I better make sure I think I went over to that third board, but just to be on the safe side, there it is. All right. So 101. So there you're like, you give it information about the limit of a function, right? But you don't know the formulas for the function necessarily, right? So it could be something like, where am I? Example 5. Suppose you have like the limit as x goes to 3 of f of x equals to 7. And you're also given that the limit as x goes to 3 of x squared f of x divided by, I don't know, 3 plus f of x is equal to, I don't know, 20. My bad. I meant to put g of x down here. Then the question is, find the limit as x goes to 3 of g of x. Now I think the problem in your homework is not this weird, but it's essentially the same like logical kind of thing, right? You've got the limit of one function given. You've got a limit that involves two functions also known, right? So how do you work this out? Well, pretty much just use limit laws, right? So this simplifies to what? This simplifies to 9 times the limit as x goes to 3 of f of x, right? Divided by 3 plus the limit as x goes to 3 of g of x. I guess I could just, let's simplify our lives. What is this on top? Times what? 7. And that's equal to 20. Because the limit, well, that's equal to 20, it's given, right? So then solve for the limit, right? Just do algebra basically. So I've got 63 is equal to 60 plus 20 times the limit of g. And so apparently, for my made-up example here, we would derive limit as x goes to 3 of g of x is equal to, let's see, 63 minus 60 is 3, then divide by 20. I get 3/20ths for mine here. What happens in that homework problem? I have no idea, but should be similar conceptually. So one we started to do yesterday, but then I chickened out a little bit, was the cube root. Let's see if we can figure out the cube root in here today. Because this will require us to do some factoring. That's a little bit different than maybe factoring you've done before. Okay. That's either a baby or somebody with an amazing baby impression, right? So. Somebody's given a test. It's here. Yowzers. Okay, so let's see if we can. So example 6, here we go. Let's try this one out. Suppose you have f of x is the cube root of x. Can we calculate the derivative function for this one? We already know it's got a vertical tangent at 0. We worked that out yesterday, right? So we know that we better limit our attention to a not equal to 0. So what are we up against here? Let's see here. So f prime of a is the limit as x goes to a of the cube root of x minus the cube root of a divided by x minus a. All right, that's one way we could try it. Or we could try f prime of x equals the limit as h goes to 0 of the cube root of x plus h minus the cube root of x divided by h here. I think this is an example where the x goes to a formalism is your only hope. I don't think anybody here is going to see how to do it in the h formalism. Even the x formalism is still a little bit tricky, but let me point out that this you can write as the following. Maybe if I do this, you'll see what to do. Check it out. This, maybe somebody here already sees it, I don't know. I don't know you guys that well yet. I don't know what you're capable of. So, how about that? How about that? Why would that help us? See, if I do that, I can think of this pattern as a cubed minus b cubed, right? Which is going to give me, you know, a minus b times a squared plus ab plus b squared, if I remember right. I always got to check myself every single time. Minus b squared plus a squared b plus ab squared minus ab. We're good. All right. You make a sign error on this identity in the middle of a college algebra lecture, it ruins your day because you are alone in there. Well, that's not true. It depends on the section. I'll have like two sections. One section I'm just alone. The other one there's like two kids that will correct me. But if you just like flip this plus to that and that to a minus, it just everything falls apart. I know from experience. So I always check. So put that into practice here. What's that look like? So we got a cube root of x minus cube root of a divided by what? Cube root of x minus the cube root of a, and then the rest of it, right? Which would be what? Like the cube root of x squared plus the cube root of a times the cube root of x plus the cube root of a quantity squared, like so. And we're pretty much done at this point, right? Because now the offending division by 0 over 0, you know, the indeterminacy here is removed, like this. Huzzah! That puts a 1 up here, not a 0. For some reason, canceling that and putting a 0 is a very popular mistake. Very popular. Don't do that. If you get 0 and it seems like too easy, maybe this was the mistake that you made. And, oh, I don't need this, right? Because at this point, we can see that plugging in a is a legit move, right? So the expression is continuous at this juncture, and let's just not write too much. Let's think. What happens? Every one of these terms is what? When you plug in a, what is it? It's the same exact thing 3 times added together, right? So that's exactly just 3 times the cube root of a squared. And this is why I didn't want to do this yesterday, because it would have like distracted us a lot. Because this is a hard one. Oh, it's a harder one. I'm not sure it's hard. So what do we learn from this? We learned that the derivative function here, f prime of x, is in fact 1 over 3 times x to the 2/3. If f of x is the cube root of x. Or if you prefer, 1 over 3 times the cube root of x squared. Okay, so now that we've done this, the next example will be like really, really easy, I think. What if we did for square root? How would the square root go? I think yesterday I did a square root which had, we did it at a number and it had some stuff under it, right? And we did it by that technique of like rationalization. But this is kind of a different way to go. After we've just done example 6, you'll probably see why I'm doing it this way. F prime of a, limit as x goes to a. We got ourselves square root of x minus the square root of a over x minus a. How's this going to go? Now, of course, we could do the whole multiply by plus the square root, right? Or we could go a different path, right? We could use our imagination and factor the denominator with roots. See? You could factor the denominator in the same way I did this one. Ooh. All right, so x minus a is the square root of x squared minus the square root of a squared, right? Which is, by the way, the square root of x plus the square root of a times the square root of x minus the square root of a. So let's put that into practice here. This is the limit as x goes to a of root x minus root a divided by root x plus root a times root x minus root a. So, yeah, what happens? Yep, cancels. This cancels that. Leaves us with a 1, right? Leaves us with a 1 up there. At which point, we can plug in a. What do we get? 1 over 2 square root of a, right? So, lo and behold, if the f prime of x function here is 1 over twice the square root of x. Now, do you have to do this limit this way? Absolutely not, right? But could you do the previous one the way that we do the square roots? What I'm asking you is, think back about example 6. For a cube root, can we just multiply by like plus the cube roots? Does that work out? By the way, what is the assumption about a here? A is what? A is positive, right? Think about the graph of the square root function. What happens at 0? Square root is half of a parabola turned sideways. All right, that's y equals the square root of x. So the tangent line at the origin is a vertical line, right? You've got that f prime of 0, does not exist. You could say it's infinity if you like. It does not exist. You got a vertical tangent. I took a point off some of your quizzes because you wrote does not exist instead of infinity. Our custom in here, if the limit does not exist, it's true that infinity is a possibility. If it is the possibility that, if it is actually infinity, you should write infinity. That's the better description of the limit. But it should be understood that infinity and minus infinity are particular cases of non-existent limits. So the best description is plus or minus infinity. I do give significant partial credit if you write does not exist in the case that it's actually plus or minus infinity. So that's why you lost just like 1 point as opposed to like 4 points for a more serious error, or 3 points for a medium serious error, or 2 points for a error, or 1 point because maybe you didn't write limit. But the charge on not writing limit might go up in time. Yeah. Okay, so anyway, example 8. Try this out, guys. What if you were to try to, and let me just get straight to the limit. What if you were to try to calculate the limit as, I don't know, say x goes to 2 of the cube root of, x minus 2. That's not what I want. the cube root of x minus 1 minus 1, say, divided by x minus 2, I guess, yeah. So this kind of problem is trickier than some of the things we've done, I think. I just want to point out to you that you cannot, the usual trick doesn't work here. See this? Like if you just try cube root of x minus 1 plus 1 divided by cube root of x minus 1 plus 1, right? If you tried that, what happens to the numerator? What happens when you multiply this stuff out? You see what you get? You get the cube root of x minus 1 squared, right? And then, yeah, true enough, minus 1 plus 1, those cancel, true, but plus 1. Oh, my bad, minus 1, right? That's how that would, this numerator, right, would simplify to that, which is not helpful because you've still got a radical. You haven't removed the radical, right? This trick we do with multiplying by square root plus something, that only works for square roots. For a cube root, or for a fourth root, or fifth root or something, other ideas come into play. And some of those are just beyond the algebra of this course if I go to too high a root. So we really need other methods to deal with these kind of problems. Yeah.
What if you did the difference, or multiply it by the other side of the difference of cubes thing instead? So you did, so instead of multiplying it by cube root x minus 1 plus 1, we did cube root x minus 1 squared minus cube root x minus 1 plus 1.
Perfect. Yes, this is the way to think about it. Reverse engineer the difference of cubes formula. That will inform the thing you should multiply. So what he's saying is, see this as a minus b and multiply by a squared plus ab plus b squared in the interests of converting this to a cubed minus b cubed, which would simplify it. That is the right tact. Right, exactly that. Excellent. I think we're out of time. Have a good weekend, you guys. Oh, the math battle is like a team-based in-class. Is that next class? I think Monday's math battle. I feel like Monday's the math battle. Don't be afraid of this. This is basically a pre-test that you guys do in a group format. All right, so to try to prepare for the test. I could be wrong. I haven't looked at the schedule. Is it Monday? Yeah?
I got it.
Tuesday? Okay.
I remember some stuff from my high school college.
Oh, and if we remember things from our high school calculus class, it is forbidden. Yes, we will not be using power rule. We have to calculate things from the limit. That is true. I was going to get back to that. Thank you for asking about that.